Hello everybody, my name is Kyle Shorey, and this is my Lab 3 circuits. So to start off, I'll introduce the lab, go through the procedure, show the models, and then go through the errors and what if and what it means. So to introduce the lab, we're focusing on using the conservation of charge through application of the node rule, loop rule, and Ohm's law. In doing the experiment, we're trying to analyze how circuits with series and parallel resistors function, utilize multimeters to measure real values of current and voltage, and investigate resistors and capacitors. Conservation of charge states that the total electric charge in an isolated system should never change, and the amount, it should essentially always be conserved, the quantity of electric charge. So these are the equations we used. So part of the preview of our results, theoretically, the currents at I1 and I2 should be equal to each other. This is for the circuits, or for the series circuit. And then you can see actually they were slightly off and slightly different from the theoretical time. And then here are the discharge and charge times for the capacitor in the RC series. Here's our procedure. So for the first part, gathering the necessary materials, connecting the materials, and then analyzing for current and voltage, and then in the RC circuit, gathering different materials, connecting them as shown here on the right, and then measuring the time for charging and discharging the capacitor for each bulb in the circuit. And then assumptions we made while running the experiment were that we had a perfectly functioning and accurate ammeter, that the resistance of wires is negligible, that the capacitor had exactly 1 farocapacitance, and the circuit had no leaks. Here are the different models. So series circuit on the left, in the middle, the RC circuit, which had the light bulb and the capacitor, and then on the right, the parallel circuit. So some of the data and calculations, as you can see, what I talked about in the beginning, the 20.4 milliamps, at I1 and I2 in the circuit, what they should be equal to, and then how when we actually measured, we got 17.1 and 17.3. And then here we have the resistors that were used. So the 100 ohm resistor and the 47 ohm resistor. After switching the ammeter to the voltmeter reads 0 volts because there should not be any potential difference across the wire. And the ammeter read 18 milliamps, probably due to just the different setup of the circuit, parallel versus series. And then you can see, ideally, if we're following the loop rule, then all of our electric potentials should equal 0. So at the battery, negative 2.6, at the brown resistor, 1.7, at the gray resistor, 0.7, and then at the ammeter, 0.079. It all sums up to negative 0.121. Pretty close to 0, but not quite. So some slight inconsistencies there. The voltmeter, so yeah. The ammeter should stay the same between the parallel and the series circuit. But yeah, in the top right here, you can see like some of our actual values compared to what we calculated. So the 47 ohm resistance, we calculated 38.8. For 100 ohm resistance, 94.4. For the wires, which should technically not have resistance, we got 6.7, or what we had assumed had no resistance. And the ammeter, which should also have no resistance, 4.89. Here's the data and the calculations for the RC circuit. Not really anything, it's just taking the times for each of them. So you can see the time for charging for both of them and the time for discharging for both of them, the 8.3 ohm and the 33 ohm light bulb. Some potential errors and improvements. If anything in the surroundings touches the system, it'd likely throw off the measurements picked up by the ammeter. Stopwatch stopping at slightly the wrong times, or misreadings on the multimeter measurements, as well as maybe small rounding errors because the numbers we're using are pretty small. And then what if and what it means. What if you charge the capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this happen in real life? Ideally, using no resistor should instantly charge the capacitor because there's nothing that would slow down the electric flow. However, in real life, this would not happen, probably due to internal resistance or resistance in the wires that connect to the capacitor. We would definitely see some kind of delay, not instantaneous. Yeah, thank you for watching.